Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 55, and it is entitled Radian Measure, Angular Velocity, and Angular Acceleration. The lesson's in two parts, and they are related to each other. The first part has to do with making motion measurements using radians, and the second part has to do with angular equations of motion. We'd like to begin this with a demonstration involving a bicycle wheel gyroscope.
You'll notice now that the sound quality has deteriorated a bit. What happens here is we have a bicycle wheel like the one that we have in the physics classroom, which is being spun up and then is going to hang by a rope and undergo precession. We say that the bicycle wheel has been given some angular velocity, and as a result, that angular velocity will cause the wheel to precess when an unbalanced torque is exerted on it. Torque is a subject of a previous lesson. We're not going to go into that in this particular course here. But this is the principle on which a gyroscope is based. The earth pulls the bicycle wheel downward, exerting an unbalanced torque on it around the pivot point of the hanging rope. The bicycle wheel has a certain initial angular momentum. When the unbalanced torque is applied, that angular momentum changes, and that's what is known as precession.
So in this demonstration, we saw a bicycle wheel that was precessing. We would refer to this as a gyroscope. When an object spins, it possesses angular momentum. That will be a product of something called its moment of inertia and its angular velocity. And angular velocity is something that we will be talking about in this lesson. If an unbalanced torque acts on a spinning object, then the angular momentum changes. This angular momentum manifests itself as precession as the spinning object responds to the unbalanced torque. So the bicycle wheel was changing its direction that the axle was pointing as it hung from the rope, trying to respond to this unbalanced torque that was acting on it. Now this lesson deals with circular motion, and there are some things we already know about circular motion. So let's remind ourselves of some things. Let's suppose that I have some object, which I'm representing by this black dot in this diagram, that's traveling with a speed v that's tangent to the circle. If the object is staying in the circular path, the direction of that velocity is constantly changing. The object is traveling in a circular path whose radius is r. We would say that this object is undergoing centripetal acceleration. And the centripetal acceleration, the formula for it is v squared over r. We've solved problems with objects that have been moving in circular paths. We've said that some objects experience something called uniform circular motion. And uniform circular motion occurs if the object is traveling at a constant speed. Most of the problems we've solved so far have dealt with uniform circular motion, or for circular motion in which we know something about the object at some instant in time, and we didn't care about what was going on tangent to the path. We were more concerned about what was going on perpendicular to the path in the radial direction. In this lesson, now we take up what happens if the circular motion is not uniform. What if the object is not traveling at a constant tangential speed? If the tangential speed, or the tangential velocity, is not steady, then not only is there centripetal acceleration, but there will also be tangential acceleration. This tangential acceleration is going to be equal to the change in the tangential velocity divided by time. But because the object is traveling in a circular path, not only will it possess these two accelerations in which the speed, the distance per time, changes, but it will also possess something called angular acceleration. And what we're trying to do in this lesson is to figure out how to handle these angular variables, things like angle and angular speed and angular acceleration. What do we do in order to be able to handle that? To do that, we're going to have to introduce something called radian measurement. So I want you to cast your mind back to your mathematics course, and let's remind ourselves about radian measure. You learned way back in elementary school that the circumference of a circle that has radius r has a certain formula. The circumference is equal to 2 pi r. The circumference is the distance around the circle if I were to take a string and measure the length of that string. The radius is the distance from the center of the circle to the edge of the circle. Now what about this 2 pi business? Well, what I would suggest to you is that 2 pi is the angular distance around the circle in radians. So that in this formula, what we have is something that relates the arc length of the circle, that's what we call the circumference, the radius of the circle, that's what we call r, and the angle that is made around that circle, which is the 2 pi. The circumference of a circle happens to be a special case when you go all the way around the circle. Well, what if you don't go all the way around the circle? Is there some relationship between the arc length and the radius and the angle? And the answer to that question is yes, there is. Before we draw another diagram, let's remind ourselves that there is a relationship between angular measurement in degrees, which is what we use a protractor for, and angular measurement in terms of radians. And that relationship is that one complete circumference in degrees is 360 degrees. One complete circumference in terms of radians is 2 pi radians, so that 360 degrees is equal to 2 pi radians. That's an important conversion factor for you. Now let's figure out what the relationship is for the arc length when I don't have a complete circle. So let's sketch our second diagram. Imagine that you have a circle that's centered at the origin and whose radius is aligned along the x-axis. Now let's take this whole circle and rotate it through some angle theta. Now an object that started at the edge of the circle when the circle began to move is going to travel through some arc length here that I'm going to call equal to s. Why s? You'll have to ask the mathematicians. That's the number, the letter that they usually use. The circle has traveled through some arc length s, a particle at the edge of the circle. The whole circle has gone through some angle theta, and the radius vector is still the distance from the center of the circle to the edge of the circle. Taking our circumference formula as our guide, we can say that there's a relationship between the arc length, the radius of the circle, and the angle. And that relationship is that s is equal to r times theta, where s is the arc length, r is the radius, and theta is the angle in radians that the circle has gone through. Some people might ask, well, what is a radian? And the answer to that question is that a radian is the angle that's produced when the arc length around the circle is equal to 1 radius of the circle. It turns out that 1 radian is equal to just over 57 degrees. So on our circle here, if I went a distance around the circle that was equal to 1 radius here, then the angle that would be produced right here would be 1 radian. One thing you'll probably want to do from time to time is to convert between angles in degrees and angles in radians. And your conversion factor, 360 degrees is equal to 2 pi radians, will be the way to go with that. So let's just do a quick example here. I'll make one up on the spot. Convert 250 degrees into radians. Well, the way I'll do it is I'll write down my 250 degrees and then use my conversion factor that there are 2 pi radians in 360 degrees. And now I'll put that into my calculator, and I get about 4.36 radians is 250 degrees. One other remark that I'll make before we go on to the next part of the lesson is that radians technically are unitless. Now you'll see that some people, including me, will refer to radians using RAD after a certain measure, but technically the radian is a ratio of the circumference of the circle to its diameter. In fact, that's what the definition of pi is. So radians are unitless. When you see someone write a unit RAD beside it, it's just to indicate that you're dealing with circular motion. The arc length relationship that we have up above here, S is equal to R times theta, basically S divided by R, if S is arc length, you'll see that referred to as linear motion, whereas the angle will be referred to as angular motion. And so when there's linear things talked about, then that's discussing distances, whereas when angular measurements are discussed, then you're looking at a certain number of radians around the circle. Let's move on now and talk about what happens when we have circular motion. And this is the topic of angular velocity and angular acceleration. There is another set of videos that I would like to introduce you to.
The speed of an object in uniform circular motion depends on the rate at which it moves around the center point and its distance from that point. Although both dots are rotated through the same angle, the outer dot travels farther in the same time interval and therefore moves faster than the inner dot. The small distance, delta s, that an object moves when rotated through a small angular displacement is r times delta theta. Dividing both sides by a small time interval gives the linear speed equal to r times delta theta divided by delta t. The angular displacement divided by the time interval is called the angular speed. The angular velocity, denoted by omega, is a vector quantity. Its magnitude is given by the angular speed. The direction of the angular velocity vector is determined by the right-hand rule and is perpendicular to the plane of motion. Notice that the vector, omega, does not point in the direction of motion, but is perpendicular to the direction of motion. Reversing the direction of motion reverses the direction of the angular velocity vector, omega. Angular velocity has units of radians per second.
Angular velocity is indicated by the Greek letter omega, and it's defined to be the angle per time. This turns out to be a vector quantity. The direction of the angular velocity is given by something called the right-hand rule. Here's what that is. I'm going to draw a circle in profile. The object begins at a certain angle, which we'll call the initial angle, theta initial. The object is going to travel through some arc length till it gets to the final position, and the angle through which that goes we're going to call delta theta, where delta theta is equal to theta final minus theta initial. That happens in a certain time interval, delta t, and omega is equal to delta theta delta t. Now what about the direction? This right-hand rule tells us that we put our fingers in the direction that the particle travels around the circle, the fingers of our right hand, and the thumb of our right hand points in the direction of the angular velocity. So omega is a vector that is perpendicular to the plane of the circle through which the object is moving. The sign conventions for omega are that if the object executes counterclockwise motion, we say that omega is positive, whereas if the object goes in the clockwise direction, then omega is negative.